let's look at the performance impacts of load to use delays. So say we have a pipeline, a processor that's otherwise ideal and has a 1-cycle load to use delay. Now on this processor we're going to run a program with 20% loads, but the compiler can only find independent instructions for half of those loads. What's the slowdown that we're going to experience because we have these delay slots? So to analyze this problem, let's first look at what all these things mean. So what does it mean that it's otherwise ideal? Well, otherwise ideal means that everything else about the pipeline except for these load delay slots is working great. So the pipeline is always full, we don't have any problems with branching or forwarding, and what that means for the pipeline is we're going to get each instruction to complete in 1 cycle. So for everything except these load delay slots, we're going to finish each instruction 1 cycle, and we're going to finish 1 instruction every cycle. What does a load delay slot mean, or this load to use delay? Well, this means that we can't forward from memory to execute. And the reason we can't do that is because the data is ready at the end of the cycle for memory, and we need it at the start of the cycle and execute. Because we can't do that, it means we have to have a delay if we have back-to-back instructions. So we can't have one instruction right after the other one using the data from the load. And what does it mean here that for half of them, the compiler can find something to put there and the other half it can't? Well, it means that we have 20% loads total, which means 10% of our instructions are going to require a no-op after them. So half of these 20% loads are going to have to insert a no-op. So we're going to insert a lot of instructions that don't do anything useful, and it's that slowdown that we want to analyze. So how do we do this? We've got 2 cases. This is with no-ops, this is a perfect case. That's our baseline, so we can figure out the performance speed up or slow down. And then this is the one we're looking at here with this processor in this program. So for the baseline here with 100 instructions, 20 of them are going to be loads, and we don't need any extra no-ops in these instructions because this is the baseline where everything works perfectly. So we have 100 useful instructions and no no-ops. We have 100 instructions, and this is an ideal processor, so everything finishes in 1 cycle. So we get 100 cycles for 100 useful instructions, or 1.0 cycles per instruction. That's the performance of this. It takes 1 cycle per instruction. Now let's take a look at this other example, which isn't perfect. So for 100 instructions here, we're going to have 20 loads, of which 10 of them are going to need an extra no-op. So this means we have 100 useful instructions plus 10 unuseful no-ops, so 110 instructions to do the same amount of work. Since the processor finishes each instruction in 1 cycle, we're going to do 110 cycles for 100 useful instructions. And that's going to give us 1.1 cycles per instruction. So this new one here is now 10% slower than the other one. So with this load to use delay, and a program where the compiler can only do this well, we've slowed down our program by 10% because of this.